Lesson 77 deals with another application of integrals, and this is going to be similar to, I believe it was lesson 74 when we talked about fluid force. You'll see some similarities here, but here now we have some type of liquid in a tank that we want to pump out of the tank, and that obviously takes work. In physics, we know that work is force times distance, and what we're going to do is look at these individual kind of sheets of liquid that we want to pump out. It's obviously going to be easier to pump liquids out of the top because it doesn't have to move as far than it would be the bottom. And so to move a weight of 1 Newton vertically, a distance of 1 meter requires 1 joule of work. And so that kind of gives us a definition there for work. To find the number of joules necessary to pump the fluid out of the tank, we use a definite integral to sum up all of these different products, these forces times distances. So force is weight density times volume. And so here we know work is force times distance, but instead of just writing force, that's the weight density times the volume. So the more volume, obviously the more force. And so what we're going to use is this idea right here that work is weight density times volume times distance. And again, what we're going to do is we're going to use the definite integral to sum up the weight density times volume times distance of all these very thin sheets of liquid that we need to pump out. So let's go ahead and we'll look at 3 examples. The first one's simpler, just getting us started off here. A rectangular tank, 6 meters high, 10 meters long, and 4 meters wide. If the tank is full of water, how much work is required to pump the water out of the top of the tank? So before we get into this example, we're going to go ahead and take a look at some things that we want to look at or do as we come across these things. So we want to conveniently place our situation on the coordinate plane. This one's a rectangle, so this is going to be placed one way. Just like when we did the fluid force, circles will be centered at the origin. So we want to conveniently place our situation on the coordinate plane, which oftentimes is putting the corner at the bottom left. At the origin. So there we have the graph that we would use. We just do the cross section here because this length stays the same the whole time, that 10. So the length is a constant. In this case, it's going to be that 10. The width is our x value. It's how far it is from here over to here. So in this case, it's a constant. It's 4 because it's always 4 wide. I know it's hidden down here, but it's a 4. And the height of the little rectangle is dy. So those 3 things have to do with finding the volume. The distance, it has to move h here. So the distance that it has to move is, this is similar to what we did before. It is the y value, or the highest value minus y. And then we have to decide on the indexes for our integral. And that's just the y values from the bottom to the top. And then we'll go ahead and evaluate the integral. So I tried to put it in pieces here. So in this case, let's go ahead and start with our integral. We want to go from 0 to 6 because it's from 0 all the way up to 6 here is the height, and it's filled to the top. If it wasn't filled to the top, if it was only filled to 2, we would actually just go 0 to 2. So we go from the bottom to the top of the liquid, not the top of the tank. The weight density for water we learned earlier was 9,800, or is 9,800, and then we have our area. Our length is this constant, so 10. Our width in this case is also a constant, which is 4. That won't always be the case, and the height of each little rectangle here is dy. It's our change in y. So there are the values for the volume. And the distance that it has to be moved, well, like if we thought about this this little sheet here maybe at 2, this has to be moved 4 meters, and what it is it's the 6 minus the y value. 6 minus 2 gives us that. So we want to do 6 minus the y value. So there's the integral that we want to set up, and then we can go ahead and evaluate it. We can bring out the 9800 times 10 times 4. That's a constant. It can come out, so that's the 392,000. 6 minus y, well, that's a fairly easy integral to evaluate. So there's the integral, 6y minus 1/2 y squared. We plug in 6, and we get 36 minus half of 36 is 18. And then when you put 0 in both cases, you get 0. So our answer is going to be this 392,000 times 18, because 36 minus 18 is 18, which gives us that it will be 7,056,000 joules of work to empty the tank, to pump out that tank that's full of water. Next example changes things up a little bit here. So a tank is 20 meters long, and its cross sections are isosceles triangles with the side lengths of 5 meters, 5 meters, and 6 meters as shown. So in this case, it gives you this shape. Sometimes it'll explain it and you have to come up with what it looks like on your own. The tank is filled with oil, so not water, to the depth of 2 meters. So it's only filled up to 2 meters, not all the way to the top. Find the work done in pumping the oil out of the top of the tank, assuming the weight density of the oil is 5,000 newtons per meter cubed. This is what work is equal to here, and then I have this to help us out, and we want to fill these things in part by part. First, we want to place this on a graph, conveniently on a graph, and in this case it's an isosceles triangle, so it's probably a good idea to put this point at the origin, and then we have a line here, and we'll be able to find the equation of this line. So I actually only took half of this here, and here's the line. Actually put in a little more information here right away than I would have preferred to. Let's talk through this though. We can see that we have this triangle here. Let's try to look at the end of this tank. We have a triangle. Oops, I didn't draw that very well. Still not very well, but and this triangle is, this whole length is 6, so this is a 3. We know this length here is 5, and so what we actually need here is this height. Well, we see we have a right triangle here. We have 3, the height, and 5, so this is going to be like a 3, 4, 5 triangle. 3 squared plus h squared equals 5 squared, and if we solve that, we get h is equal to 4. And so this height here is 4, which means this line, or this side of this triangle, is a line, and we can find the equation of the line. The reason it's y equals 4/3 x is because our slope, we're going through 0, 0, and it comes up here. We went up 4 because of the height we just talked about, and over 3 because of this length right here. So you will have to figure that out at times when you're working through these. So what we want to do here is we want to figure out the integral here. So I'm just going to find the work done doing half of it, and so I have this 2 multiplied out here. I think that will make it easier than trying to add the other half in here and find those full strips. So we have 2 times the volume of just this right side of the triangle. So our indexes are going to be 0. I'm going to be going from 0 to 2, because remember, those indexes have to do with how high the liquid is, not necessarily how high the tank is. So we're going from 0 to 2. Our weight density, we were told, is 5,000. The length of this is a 20-meter trough here. The width, well, the width is changing. The width is the x value, and so we want to know what that x value is. So it has to do with this line. This is y equals 4/3 x, so we want to go ahead and solve this for x. So solving this for x, we multiply both sides by 3/4. So we get that 3/4 y is equal to x. And so x is our width. So we put 3/4 y in there. And then the thickness of each of these sheets that we're looking at is change in y, or dy. And then the distance that it needs to travel, well, it needs to travel our 4 minus our y value. 4, the height of the tank is 4, and we're going to subtract whatever y value we're at. And so that is the integral that we want to evaluate. And evaluating it, again, shouldn't be too difficult to do. So first we can multiply 5,000 times 20 times 3/4 and bring that out and multiply it by 2. So we get 150,000. And then integrate from 0 to 2 of y times 4 minus y, 4 minus y dy. We'll go ahead and distribute that y. So we have 4y minus y squared. And now we can find the definite integral. I don't know why that extra little line is there. So this is 2y squared minus 1/3 y cubed. We can plug in our value 2. Putting in 2, 2 squared is 4 times 2 is 8. Putting 2 in here is 8, so 8/3. And then putting in 0 again gives us 0 like the last one. 8 minus 8/3, well, it's 8 minus 2 and 2/3, which is 16/3, or 5 and 1/3. We can actually reduce here, so 3 goes into 150,000, 50,000 times, and then we multiply, and we get 800,000 joules. So the new part was done up here. The rest is just evaluating an integral, a definite integral, which we've done many times before. Our last example here, the end of a tank is a semicircle whose diameter is 20 meters. The tank is filled to a depth of 4 meters with a fluid that has a weight density of 6,000 newtons per cubic meter. Set up an integral that could be evaluated to find the work required to pump the fluid to a point 20 meters above the top of the tank. So a couple new things here. We have a cylinder looking thing here, or half a cylinder, and then we're not just pumping it out of the top of the tank, it's going to have to be 20 meters above the top of the tank. So again, this is what we want to do. We want to integrate weight density times volume times distance. This is circular, so we're going to want to graph, and we'll put our center of the circle at the origin. And we want to pump something up over 20 meters above the top of the tank. So here's our circle. It's a radius of 10, well, diameter of 20, so radius of 10. So the equation of this circle is important. We'll use that later. The equation of this circle is x squared plus y squared is equal to 100. Because it's equal to 10 squared. 10 squared is 100. So we want to integrate our values here. Our values, once again, kind of like the triangle one we just did, I'm just going to do half of this. You see the light gray here. We're going to do half of this, and then we'll go ahead and double it. So that using that same strategy. What are we going to integrate from? Well, our lowest value is -10. And then it says the tank is filled to a depth of 4 meters. So it's only 4 meters deep. So we want to go 4 meters above -10, which is -6. So we only integrate for the fluid. We won't go from -10 to 20. That's a mistake that's commonly made. Now plugging in the other stuff, our weight density is 6,000. The length, so our volume is next, the length is 40. The width changes. Again, the width is the x value. So once again, we want to solve our equation for the x value. Before we had a line, well now we have a circle that we want to solve, and we would subtract y squared. Subtract y squared, so 100 minus y squared, and then we would take the square root of that, and we get x equals the square root of 100 minus y squared. So that will be our width, and then the height is still dy, and then the distance that it has to move. Well, this is an interesting one. So normally, if it was just out of this circle, we would have to move negative y, kind of like before when we dealt with this. Well, it has to move negative y plus 20, or we could think of 20 minus y, because at maybe this height of negative 10, this very last drop, it has to move 30. Well, how do we get that 30? It can be 20 minus negative 10. And so that will be the distance we have to move it. So we mentioned the volume has to be 40, the length, the width, and the height, and then the distance that it has to move is going to be 20 minus y. It actually just said set up an integral that could be evaluated. So this is all we need. We could clean this up a little bit to make it look like a integral that's about to be evaluated by bringing out the 6,000 and the 40. So we would have 480,000 and then times this integral. If you did want to evaluate it, you would get this 296,621,705 joules. And so in this lesson we worked through using integrals to find out how much work is being done to pump fluid or liquid out of different types of containers.